welcome back to my channel. I just think of different things I want to talk about every day, and today I want to talk about putting a secant on a Desmos graph. Now this might help people think about their early stages of calculus. It might help teachers teach calculus. I don't know. It's quite a useful exercise to go through when we're thinking about elementary gradients on curves. Alright, so first of all, what is a secant? Well, it tells us here from Wikipedia, a line intersecting 2 points on a curve is called a secant line, and you can see there the secant line goes through, in this case, a circle, and it continues beyond each end. Alright, so I want to put a secant on any curve on Desmos. So let's get straight to it. Let's create a function f of x, and let's make a simple one. So I'm just going to start off with x squared so we can see the steps through this procedure. So there's my function, f of x is x squared, simple parabolic. The next thing I want to do is put a couple of points on this line, points P and Q, and I want P to be 1 point and then Q to be a little bit along. So let's just go right ahead and do that. But I'm going to have to put these in terms of variables. So point P equals the coordinates A and f of A. Right, put a slider in. Let's label this point capital P. Alright, and you can see there, point P moves along the curve, right? If I make P equal to 1, no, I'll make it equal to 2. So I make A 2. 2 gets plugged into my function f of x. 2 squared is 4. So the f of a, if a is the input, the output's 4. So a goes in, the f of a comes out. 2 goes in on the graph, and 4 comes out there. Lovely. So that's point P. Now I need another point, Q. Now this one, we need to give it a little nudge on the x-axis. So that's a plus h. And the output is, well, if you've done your elementary calculus, it's the f of a plus h. Right, so this time the input is a little nudge along from a. And in this case, my nudge is, I can change it, right? I can change it with that slider. In a minute, I'm going to label that Q. So that's a little nudge along from x, alright, it's x plus a little nudge, and if I put a secant through both these points, I can get a good visual idea of what the gradient is representing as, h approaches 0. So let's carry on and do a gradient function. That's going to be m equals, well, again, you should know this, it's going to be the f of a plus h. Normally we use x plus h in class, yeah, but minus the f of a, and all that's got to be over h, right? And if you remember your limits, as h tends towards 0, I'm getting a gradient function outlook, and I can see there the gradient's 3. If I change this, the gradient increases, and you can imagine a line or a secant between P and Q, cutting the curve at 2 positions, P and Q. As it gets closer, it gets less steep. If I bring P and Q down to the bottom, you can see the gradient goes to 0, as it's at the bottom of that curve. Okay, so gradient function m. Now the last bit I need to do is create a line joining these 2 positions, right? And that's going to be, I'm going to flip to this y equals mx plus c, the coordinates through a straight line. If I rearrange this for c, the y-intercept, and I put c in terms of a and h. So x is a plus h, y is the f of a plus h. Substitute them values in, so y becomes the f of a plus h. mx is m brackets a plus h. Substitute this value of c into the original equation, mx plus c, so we get this. Right, rearrange that equation to group my m's together, I get this. Take m out as a common factor, I get this. And I'm nearly there. I just need to distribute this negative sign through the brackets and I get the final thing is this. Now if I can just paste that straight into there. Beautiful. There you go. There's me secant. Right? You can see the secant cutting 2 points. And I can use this as, so if I just put P there, as Q, as I bring H down and get H very, very close to P, you can see the value of this secant becomes the actual gradient. And as the limit of H approaches 0, the value of that secant comes to 0. Now, I used x squared before, but I can actually use anything, you know. I can use a sine wave. And that gradient can represent, for example, you know, when you're talking about EMFs created by a change in magnetic field, you could use this, the gradient function, you know, d, if this sine wave represents the magnetic flux, the change in magnetic flux would be proportional to the voltage. So at this point in time, there or there, when the gradient's maximum, that would represent peak induced voltage, right? And at that point, it would be 0. Anyway, so that's how, maybe this gives you an idea of how you can create a secant, program a secant into Desmos using some pretty simple algebra, really. Alright, I'll call it a day there. Thanks for watching.